it works. I need to acknowledge fantastic team in Liverpool, plus Ronan, STFC. Adam did most of the heavy lifting this time. He can't be here, but Philo and Lucar, so chat to them. We're funded and linked out to CCP4 and CCPM, and I also want to thank Andre for patiently dealing with innumerable questions. So this is what I'm going to be talking about. We're here to assess the single chain tertiary structure. So we need to decide on what our score is meant to be. We're considering whether we should change the score with respect to side chain into the hangover issue from last time. We also decided to consider whether to include a new measure in the calculation. I'll talk about the rankings. I'll talk a little bit about the CASP15 to 15 comparison. This is a very hard thing to do, of course, because the targets are fundamentally different, but I'll do my best to discuss that. We'll talk about different kind of approaches and their ability to self-assess, and that's where you'll hear a little bit more about how the language models did. We'll talk about where the remaining issues are, so where there's still room for improvement, where there are local errors, what local errors are caused by. Talk about side chains and how well they're predicted, and then finally ongoing applications, not including functional prediction, which we looked at, but which I don't have time to talk about. I'll need to probably gallop through these slides in any case. So, choosing a score to rank the groups by, we looked back to previous CASP for the easier template-based modeling targets, and the logic there wasn't given the progress that had been made so rapidly. It seemed fair to tighten the scoring and assess even the hard targets by the criteria that were previously used for the easier targets. So this is what the template-based modeling was assessed with previous CASPs. There are local, backbone, and global scores. Then in the last CASP, there's an extra little bit in the backbone scoring. So we wondered whether to include extra weighting on the side chains. So there was a side chain element to the previous CASP scoring. We could consider but greater decline. If that's the definition of it, it's quite a sophisticated one. It considers variable and recognizes the fact that predicting chi2, well, if chi1 is inaccurate, is pretty meaningless, so it's quite a sophisticated measure. We also looked at whether we could include a different measure, which included all of the chi angles, because the existing scoring is only chi1 and chi2 based. We thought maybe we should look at the rest of the project as well. And we also looked at this side chain measure, which is available on the CASP automated website. Long story short, we didn't change anything because the weighting, even if we changed the weighting of the existing component, nothing much changed with the ranking, and the two candidate additional scores for side chains were too closely correlated with elements that were already present in the scoring system, so it didn't make sense to add that. RALOG is a bit different. RALOG is a new criterion metric calculated on the CASP website. It predicts the ability, the usefulness of models for molecular replacement, which of course is one of the principal ongoing applications of all these kinds of models. It was also the only place at which the atomic PLDDT estimates, which predictors were asked to provide this time, were taking it to account. And so between those, we were inclined to include it because it's the only way in which we look at the atomic PLDDT, which also recognizing the importance of MR. So we considered adding it to the global measurement part of the equation. And in the end, we chose to do that. We checked whether it made a huge difference to the score. It didn't make a huge difference. It made some difference. We thought it was a good idea to include, and I should say it wasn't too closely correlated with the existing method. So we included it, and this is our CASP15 scoring with that changed, that part of the to include RALOG. This is just a reminder that the CASP15 rankings are calculated on Z-scores, and Z-scores that are calculated in a slightly complicated ways, first discarding outliers and recomputing, and the final score ignoring any negative Z-scores in order not to discourage people from being adventurous in that the model's placed up at. And it's also a reminder that in the final rankings, we decide to add together the Z-scores rather than consider some kind of average, because we want to reward the groups that are predicting consistently across a large number of models. targets, I should say. So this is the ranking we came up with. So different to last time, we don't have one single standard method. AlphaFold 2 last time, of course. Instead, we have a number of groups. We have a large number of groups. A number of groups take extremely well. A large number of groups get pretty well. And a sort of gentler profile. These are the groups that you'll hear about later on, and just a few of the key characteristics. Interesting to note that they all pay special attention to the MSAs that they produce, which I think is significant. And also, I thought it was really interesting that two of them look back to previous generations of modeling software in the shape of INTAS or TR Rosetta to combine with some elements of the AlphaFold 2 data prediction. So there were two kind of benchmarking representations of AlphaFold 2 within the set of predictors. The standard AlphaFold 2 was run the NBIS, and correlate fold was also submitted as an automatic group. They're color-coded in green in these slides. Blue are human groups, are red are stirs. And I'm also picking out, we'll talk more about these methods later on, but the top language method by this ranking was DSM single sequence. But you can see it's relatively far down the list there, and we'll talk more about that later on. Just to show you in passing that if we use the previous CASP15 and CASP14 measures, we don't see radically different rankings. We can also look at which groups produce the best models for a given target, and we can use our CASP15 score, or we can use the GDTTS, which, remember from yesterday, simply measures the overall fold, what the quality of the fold prediction without worrying about the fine details. The ESM single sequence actually gets the best model for 4 of the different targets. And it's interesting to see where the correlate fold of the standard AlphaFold 2 are the ranking on the right as well. They're relatively higher there. One clear message that came out was that servers are now very competitive with human groups. So if you look back at CASP14 and 13, the red or the red markings of these graphs, humans always did significantly better. So where it was human expert input, the groups to form them, that's much less the case, if at all. Now we can see at the top 3, there are actually 2 servers, only 1 human group. And furthermore, we can look at kind of pairs of submissions where there's a group that had an automated submission and a human submission, and we don't see a consistent advantage of the human one anymore. Not that we can detect, really. Right, so I'll spend a bit of time on this one. You're all familiar, I think, with this kind of graph, which tries to capture how progress has been made from one CASP to another. There's a few things to show here. If we look at the CASP14, which is the solid blue line, the CASP15, this time the solid black line. If we consider that line is generated for the best model fit across all groups, then broadly performance seems to be comparable. Those 2 lines are in the respective place. But the picture is a bit different if we consider the best groups. So the best group last time was almost exactly CASP14 blue solid line, because the best group was usually AlphaFold 2 last time. And if we look at where the best groups are this time, there's a little bit of a drop-off, it would seem. So the best groups are the Yang server, PZ folding, the ZUAP-TVM. Those are these lines here. And they're just a little bit below where AlphaFold 2 was last time. I should say the target difficulty here. The target difficulty is calculated on the availability of templates detectable by sequence or structure methods, so it doesn't include a number of other factors which I'll come on to in a second. And the terms of AlphaFold 2 controls in the shape of correlate fold and the NBIS AlphaFold 2, they were significantly off the pence with respect to the top groups there. So this was perhaps a little bit surprising, demanded some kind of further investigation. And so what CASP as an organization did was invite DeepMind to look informally, because DeepMind an end to the competition, but informally after the fact they were invited to look at the targets and try to understand whether they could have done better than, for example, the internal AlphaFold controls. They did do better, and I'm not going to show their results because they weren't an official participant, of course, but broadly speaking, the DeepMind's informal submission was at the level of the top groups, but it certainly didn't make it quite to the level of CASP15 last time. What might explain why the gig for DeepMind submission did better than CoAlphaFold and the AlphaFold 2 or rather NBIS? Well, they retrained the network. They did some increased sampling and crop size. There were also some possibly key human interventions. So important to remember that DeepMind is a human group, and these internal controls were automated. So that still leaves the question as to why the best groups this time were a little bit behind the best group last time. And one possibility, of course, is that the CASP targets this time, which are a completely different set, were just a bit more difficult than they were previously. I'll come into some more detailed thinking about that. This is just to give you an overview of the results. Of course, you can't see anything here, but we've got groups on the bottom, got targets along there, arranged vertically. This is by GDTTS, so good is red, bad is blue. And with respect to targets, we have a block of targets at the top, which are very difficult for most methods. And we have a large majority of targets, but a large majority of methods did very well. We have a few methods on the right-hand side, which were one bit below par or below one. The other methods, we have the grey on the left-hand side of methods are submitted for multimer predictions only. So I just want to extract a few of this to get the micro methods from the servers coloured blue and red respectively on the top. They're kind of distributed throughout, so there's no consistent feeling that humans do better. An important message is that most of the top methods did use AlphaFold in some form, so we analysed how they used AlphaFold, but just as a yes/no in this column here, you'll see that most of them use most of them use AlphaFold. And if we look at the block of targets that were consistently difficult, and we look at this first column here, we can see they are as remodeling targets. So that sort of classification that Andre explained yesterday, that's still important and useful as a guide to where methods might struggle, even though it only captures the availability of templates. That still seems to be an important predictor of where there are targets that might prove difficult. We also noted the phylogenetic origin of the targets. We see that virus targets are enriched in this set of difficult targets. And this just talks a little bit more about the classification Andre introduced this yesterday, but what we looked at was a fair comparison of the CASP15 targets redefined automatically in the way that Andre explained. And what that reveals is that we have a lot more free modeling targets this time, so a lot more where there's no obvious template. And these have the potential, they're not guaranteed to be hard cases, they have the potential to be hard cases, I would say. So, a little bit more on what we could correlate with down the average, and essentially sort of very case-specific and difficult combinations of aggravating the factors that what we found. So, I decided to get a very clear explanation of that. So performance of different kinds of methods. We fed that heat map into some PCA analysis, and the best methods were clustered together. The internal control was in terms of standard AlphaFold 2 were a little bit distant. Two interesting observations. One is that Baghdad group, which is the top group that doesn't involve AlphaFold in any way, they cluster with the best methods. Whereas the language model groups, they lie in different places in the plot, which I think is quite interesting. That suggests that maybe they have different strengths and weaknesses and perhaps the potential to combine them in the future. Which targets do their language models do well? Well, these are extracts from the heat map for 3 language models. You remember that ESM was the best by CASP15, but we noticed when we looked at the GDT profile that this UN-res actually got better GDT scores than ESM for a number of targets. So we looked at that in a bit more detail. EBBA was also there, that seemed to be a little bit off the pace, so we didn't look at that. We looked at the 4 cases where ESM single sequence produced the best model. 3 of them are illustrated here, but not allowed to show the 4th. This one, for example, is a free modeling target, so there's no templates for this, which shows, of course, that the language models can generalize beyond what's learned. One specific point that people are very interested in, the language models have any advantage with target that have low NF, so singletons or shallow alignments. The answer from the data that we have is no, apparently. So, sorry, I lost the formatting slide, but these targets are rounds according to NF. So here on the left are the ones with lovely deep alignments, and the right you have the singletons. You have 2 methods in blue which are NSA-based, and the 2 methods in red which are language model-based, and this is GDTTS. So the language model wins in a few cases, but not in cases that are particularly skewed to the right, where NF is low. The language model wins on the very hardest case on the right, but all models are poor in that case. And in fact, if you scan your eye across, the red seems to be lower on the blue systematically on the right, compared to on the left, which suggests that, if anything, tendency is the opposite. But where we have low NF, the slightly lower performance of language models is exacerbated. And also, just following the track across, it does seem to be the case that where the MSA-based methods struggle, we also see the language models struggle. So where there's a kind of dip on the blue, MSA methods don't do so well, we typically see that the language models also don't do so well. In terms of how groups assess their own performance, I won't spend too much time on this. They were not especially good at picking out the best model as model 1. So on this graph down here, for example, if a group submitted 5, then they'll get the model 1 will either best 20% of the time by chance, and there's only sort of slight bias above that 20% threshold. Perhaps a better way of looking at it is this kind of graph where we have the best model TS GDT on the x-axis and the model 1 on the y-axis. So anything below the diagonal is where there was a better model available to a group than they submitted as their model 1. The best MSA groups are at the top here. You can see sometimes there were models available to them that they didn't put at model 1 with GDTs that are 20, even 30 points better. And the same with the language models. And they were asked, of course, to submit atomic PLDDT estimates. Those were only evaluated at a residue level. That gives us a ranking based off the ability to self-evaluate confidence. And I think the interesting thing to say there is the best groups by CASP15 rankings were not necessarily particularly good at self-evaluating the residue scores. So our interface is still a problem. This was something we noticed in the last CASP, but I'll come to that. Right, so we can imagine that residues that are at an interface, be it a crystal lattice interface or an interface with another chain. They might be particularly difficult to predict. In the case of a crystal lattice, that's simply not factored into the calculation at all. In the case of a chain, you're depending on accurate modeling of the intermolecular interaction and so we looked at this. So we collected residues across long ones, which were of decent quality. So we're not looking at the failures, we're looking at models that were pretty decent, but which still had residual errors within them. And we say, is the error greater at a crystal lattice interface or at a chain interface than it is in residues in general? These are the counts, these are the statistics. And the answer is yes. Across all of these individual methods, the crystal lattice contact residues have a higher error than residues in general. In fact, most of these comparisons are statistically significant. And funnily enough, the ESM single seal, which seems to have a particular issue with chain interfaces, don't know what that means. And we did a similar analysis on errors, so the regions of 3 or more residues that were slightly out. Are these found at crystal lattices? Are these found at other interfaces? That's the definition of what we call an error. And the answer is yes. So we look at the top method as an example, piece controlled straight by the formatting. About a third of the local errors, 3 or more residues that are significantly out, were at a crystal lattice. So that's clearly more than we'd expect by chance. What are we talking about here? We're talking about structures where, like this, we've got the experimental structure in blue, we've got the error region in red. You can see this is an error, but it's an error because it's kind of unaware of where the crystal lattice makes is here. So it's occupying space that's occupied by the symmetry domains in the actual crystal. We also looked at B factors, so our flexible regions in proteins where that flexibility is reflected in a higher B factor of the crystal structure, and they're more difficult to predict. And the answer is again yes. So across all of these methods, the B factor is high, implying it's a local flexibility, and the error is also high. Side chains, we looked at we used the squirrel score to say, is this side chain basically correct? And spend too much time on this, but basically the correctness only goes up to 80%. But of course, we need to remember that side chains, as a solid exposed to the surface, don't necessarily have a single conformation. So we perhaps don't expect to reach 100% for this. Perhaps more interestingly, do you need to predict the main chain well in order to predict the side chain, or are these correlated? The answer again is yes. So we've got a side chain dihedral score on the y-axis and the main chain dihedral score on the x-axis. And where you see this is upon the basis of modulus rather than residues, where you see an accurate low score for side chains, that is only seen when the backbone is accurate, which is kind of perhaps what you'd expect. We see the top groups do better in that respect as compared to submissions as a whole, which is no surprise. This is comparing MSA-based methods and the language model methods. So long story short, the language model methods don't seem to do as well with side chains as the MSA-based methods, which are based on AlphaFold, of course. And has the quality of the side chain prediction improved since last time? Well, the answer is a sort of probably a little bit. So here we have CASP15 AlphaFold 2 against the best 2 MSA-based methods this time, and the profiles are slightly shifted in the favorable direction. So I lost track of time here. How long have I gone so?
-4 minutes.
Yeah, that's technical. Sorry about that. Well, I just skipped through, I just described what we did without entering into too many details. So we looked at models versus molecular replacement. basically the message is that models are very good. And if you talk to any structural biologists, they'll say this, that most crystal structures are stable magnet replacement relatively easily. So we looked at the LLG for an ideally placed model. And for many targets, this is one target model. Most groups, if you place their prediction, ideally, they're above the threshold for some successful MR. And if you go ahead and do the actual MR experiment, which is important because when you do the experiment, you might run into packing issues and things like that that are not obvious unless you actually do the MR. The message is the same, but for many targets, the models aren't good enough, straightforwardly. But there are cases where you still, where given targets, a given method is not quite good enough, or where you need to work a little bit harder with the result of a given method. For example, trimming off the lower quality, the lower confidence regions in order to get a better solution. This just highlights one particular target where you need to process the model into a domain. There's a slightly harder target, so mostly the unmodified predictions are below the line. I'm just showing as an example for the SM single sequence here. The unmodified model is not good enough, but if you trim it, if you process it, I should say, into several different domains, you can fit those domains. Slice and dice our software in CCP4 is one way you can do that. So here is the original model. The domains are accurate within themselves, but they're placed inaccurately. You need to split them up, whereupon they can be placed accurately and solve the structure automatically. So this is a ranking of groups according to the LLG. We don't know quite what the best group did because there's no abstract, sadly. And then, very briefly, we did something similar for cryo maps. We placed them through the assessment units into the full and segmented cloud maps. Now, this is Luke's work. You can talk to Luke about this. He had to modify the scoring to distinguish between cases like this, where the fit is quite good, and cases like this, where it isn't. And he could also produce a ranking, and the beta group happened to be top in that ranking. Again, slice and dice is necessary where there are domains that are incorrectly positioned. So this is the original structure. You can slice it up, the slice and dice, and then that domain fits much better in the back as a result. So, apologies for overrunning. These are the main conclusions, I think. There's no single method like last time. You've seen the several methods before very well. We'll hear why in a second. AlphaFold 2 is the basis for most of the best methods. Now, servers do much better in comparison with human groups than they'd have in the past. The language model methods are not generally quite up there yet with improvements of prediction accuracy. But we have to remember, I think, that this area is much younger and gives that more time to develop. And, of course, some of these models are extremely fast, and I think that innate speed, even if the quality is not perfect, will enable some interesting applications. In terms of ongoing applications like lead replacement or cryo outfitting, many methods, including the language models, are very good for these, but as I showed you, sometimes you need to process them to recognize the fact that domains are not well predicted with respect to each other, their relative orientations. And that's where I finish things.
Okay, thanks, Dan. Thank you very much. It was great. Unfortunately, because of time, I think we need to move on. We're going to discuss all this evening. So let's move on to first of our two talks on assembly assessment from SG.